Good afternoon. All right. Remember yesterday, each one of you were given a card, and it was for class attendance and also possibly answering math question on the board. You guys know the pretest. We talked about the pretest. It's in Georgiaville under quizzes. It's a assessment test, so it's not a grade that will affect you, but it does provide information that we can compare. So we're gonna have a post test in April. So now I'm hoping that you guys are gonna take the pretest. It's okay if you haven't taken it yet. It's gonna be open for 14 days. But I'm gonna use it for attendance. So you can answer yes or no. If you wanna answer yes, it's A. If you wanna answer B, it's no. Any report the attendance or not? This is pretty much a survey. But once your name is highlighted, I kind of know that you at least the attendance is recorded. So it looks like we're missing 3 people. They were there yesterday. So it looks like only 2 has taken it yet. So I mean 10 of us haven't taken it. I looked up online, there are 4 that was already submitted. So I think 2 of them are not here today. Anyway, try to take some time. It's not a long quiz if there's only 8 questions. Try your best. You may feel like some question looks familiar but not so sure. But it's okay. Just try to finish the quiz and then that'll be it. It's not for it's not count against you or for you. It's just for like a data. It's a data that we can work on. Right. So another thing is we did try to introduce Webwork. Have you tried logging into it? I think I haven't really added you yet, right? I should do that. Yeah, I think I remember the card, but somehow to the Webwork thing. So I'll do it right after class. Sorry, that's something that we should practice. All right, today we're gonna really work on the actual calculus stuff. The first thing we're gonna talk about in the calculus class in chapter 1, we're working on limit. So first, let's try to actually load up the file. All right, class material tend to be not as extensive. So if you feel like you need more example, more exercise, you can try to read the text. The text is in Georgiaville. The textbook is already, it's a e-textbook. If you prefer a paper copy, I think the bookstore can help you order one. And all right, so first section, let's introduce the idea of limit. This is actually the informal definition, informal way to introduce limit. But first we have to kind of know what it is and how to calculate it. All right, so here is explanation for the term calculus. Occasionally we get, what is calculus exactly? What does calculus mean? It means a method of calculation and reasoning. And you can see the word calculus has calculation in there. So it's related to calculation, but with with more to it. I start with a definition for the limit. We actually start with the notation. That's how the book does. But it does feel like it's introducing some new terms, some new way to represent things. We did a clear question earlier, but you guys can stay a little longer after class to answer the clear question.
Okay.
So we're gonna talk about informal definition of limit, and then there is also a formal definition of limit. So first we need to know the notation. So whenever you look at a notation, the limit notation, it looks like this, LIM, and then a formula, and then below the LIM where there's X with a little arrow to a number, and then you get another number on the right side of the equation. So the limit notation looks kind of like a, because I'm recording this, so I'm trying to write everything on the board or on the computer, so it's actually in the class recording. So it looks like this. Type. Right, because it's in the classroom, I'm trying to write as big as possible. So LLM is a notation indicating, hey, we're finding a limit on something. We try to make an example. In the text it goes like this. LAM and then a formula, I mean f of x, that's really the abstract way of saying, hey, we got a formula here. And then right now we just write f of x in its place. And then below the LAM you have x, which is the variable name. Your variable can be other letter like y or t or u. But for now, the most common variable in math, we use x. So x is a variable. What is a variable? Variable is kind of like the root of the word variable is vary. So it is a quantity that may be changing. So for now, this quantity is approaching, the arrow saying that quantity is approaching this number c. And c again is an abstract way of saying here you're going to put in the number there. So x is approaching this number. We're saying limit of a formula, limit of function is going to this number. And that's really the notation. So we introduce limit notations so that in the future, when you write down the notation, you know that this is the limit of something which had this value. And then, as always in mathematics, whenever you introduce limit, one of the purposes of using notation is to say things in a really concise way. Okay, so I'm writing something more specific. For example, I can see limit of x squared. It won't go where I intended to go. Somehow I'm trying to write x squared. All right, this is supposed to be my f of x. New Windows changes things. All right, so in the abstract notation, we have limit of f of x. But if you actually are going to do some calculation, your f of x has to be meaningful. Right now, the f of x notation is limit of this function equal to this number L. It's all like hypothetically speaking, abstractly speaking, but when we are doing calculation, we actually have to have something to work with. So this is my f of x, all right? And then down here, we have the x value, which should go to somewhere. And change the color to full white. I'll just write x approaching. I'm drawing, really bad at drawing with the computer mouse. X is approaching a number. Let's say x approached 2. Okay. Now, so this notation is kind of like asking, when x is approaching the number 2, what is the limit of x squared? Okay. What is the value of x squared approaching 2? Guess what's the answer? If x goes to 2, what does x squared goes to? 4. Yes, exactly. So sometimes it's not that hard to figure out the answer, especially when the calculation involving the formula like x squared is not a very complex calculation. You just take a number and square it. That's pretty much the calculation. So right now, this is our first example on limit notation. And that is saying limit of a function x squared when x is approaching the value 2, x squared is approaching the value 4. Any question? Right, we're just using this example to be more familiar of the notation. Just want to make sense of it. The actual notation in the book is this one, which meaning that f of x can be any function. It can be x squared, x plus 4, x cubed. F of x can be anything. Notation here means that limit of f(x) as x approach the number c. C is a number. I had c equal to 2, but c can be 1, c can be 0. But this notation here just indicating that this is a general idea of a limit notation. As x approaches number c, the limit of f of x equal to L. That's limit of the function equal to L. The informal way of seeing it, the limit actually is not as simple as calculating x squared, 2 squared. It actually means the process of approaching. You're gonna have to the word approaching as x gets closer and closer to the number c. The value of f of x gets closer and closer to the number L. We can make an example out of our question. So we're saying x approaching 2, meaning that x is getting closer and closer to 2. We see the tendency. So for example, if x equal to 2.5, all right, and then what's x squared? X squared is 2.5 squared, which is like 6.25. All right, and then if x, let's say x is getting closer to 2, a little bit closer, such as x equal to 2.1, then x squared would be 2.1 squared, 4.21. What is it?
4.41.
4.41. All right, and then we can get even closer. So the point is to understand limit is actually a process. It's not as simple as just calculating x squared. So then x squared would be 2.01 squared, which is really close to 4 now. This is like
4.0401.
4.04. Thank you. So as you can see, if x does equal to 2, the x squared will be 4. But then you can see, as we see the process, if you're making x, this is just whatever, I'll pick a random number. But if you want to see the process, you can do 2.6, 2.2, 2.3, and 2.001. But the whole point of seeing that when you are making x approaching 2, your x squared value is approaching closer and closer to the value of 4. Think about limit as a process of saying that if x gets closer and closer to 2, and the y value is getting closer and closer to the y value of 4, to the x squared approaching 4. So this is our informal definition of it. And we have a couple of other examples to see that a lot of time, as simple as what we're doing, approaching, making x equal to several values, allows you to estimate that process of approaching the number. So here we have this question, all right? That's when x approaching the number 1, and if you see the x approaching 1, this is something you can try on your own. Use your calculator. You will sin of 1 over 1. Make sure your calculator is in radian mode, because if the calculator is in degree mode, sin 1 is different. Maybe sin 1 degree. If calculator set in radian mode, then sin 1 is roughly 0.84. Do you guys have your calculator? Was it 0.84 something? Was it?
Yeah.
So it is roughly 0.84. That means this question, we are able to get to the answer with plug in x equal to 1. So we have sin of 1 over 1, and pretty much is 0.84. But on the right side, we have a slightly harder question. And that's why we have to think about the limit as a process. Because if you make x approach 0, sin 0 divided by 0, that is a division by 0, meaning that we are not able to get an answer. by substituting x equal to 0. So that is saying if you are trying to find a limit value of a function, this function just might possibly be undefined at 0. Because when you think about limit of something, we're not guaranteeing that f of c actually equals out. We're not saying f of c does exist. All we care is the neighborhood in that region. If x approaching c, the f of x is approaching L. That's all we need. So we don't have to do this calculation. I mean, that's something that we were doing on the board, and except I didn't do it in a table format. Let's do it ourselves. All right. So what we're doing is this side of the calculation. I mean, what we can do is like you see that you can make x approaching 0, but what we can do is we make x equal to let's start with 0.1, and then you're going to calculate sine. Now, if you have your calculator to try it, make sure your calculator is in grading mode. This one too are really small. So try using a calculator. All right, make sure your calculator is in grading mode. If you're trying it with me. So we're going to do sine 0.1 divided by 0.1. Because now our x value equal to 0.1, and then you can see it's what it is. This is supposed to be what's on your calculator if your calculator is in the right mode, right? It is.
Yeah.
And then you can see we can make x equal to either closer to 0, even smaller numbers, x equal to 0.01. Then you're going to use your calculator and calculate sine 0.01. divided by 0.01. We're going to have to do both of these two x values have to change simultaneously, and that will equal to the second number, that's 0.99998334. And then if you make x equal to 0.01, it's going to be this, right? It's even closer to 1. 99999, and then 8333. Except you can add more 0. You can make x equal to 0.0001. But then the calculation is going to be a bit more tedious. It's going to go sine 0.001 divided by 0.00001. The more 0 it is, the more closer you get. The thing is, if you put it into your calculator, make sure that it has the same amount of zeros, because it really changes the number entirely if they're not matching. Make sure this two matches. And whatever you do, as you add more 0 to it, this number is getting closer and closer to the number 1. The truth is, limit of this entire division is equal to 1. And you can use the calculation. What we are doing is called numerical exploration, because obviously the amount of zeros that we're adding, it can be as many as you want to. Sometimes our calculator lost track of the 9s, and then the calculator will just give you a number 1 if you put enough 0 there. But if x does equal to 0, it's undefined. So function itself is undefined at 0, but limit do have a value limit for 1. This is a numerical calculation for a limit. Any questions? This is our first situation, thinking about when the limit of something is difficult to calculate. What can you do? One of the things you can do is, if x is approaching this, I'm making x approaching it, but you're going to have to do it in a process. So you can't just use a single number. You have to use a couple of numbers to see the true tendency. If you only try one number or two numbers, sometimes it could be misleading. So to see the tendency, you have to use many numbers. That sometimes can be a little bit time-consuming, but you're going to have to run through the process to guarantee that the limit is that number that you anticipate. But then again, if you substitute a number and then somehow you already have the answer, this is the kind of situation where you really don't have to do anything further because calculation, the substitution actually worked. Any questions? Difference between the two is you see we did change one little number. This one x equals to 0, right? And it's undefined, and then we do all that trouble. It goes through all those calculations to get to the limit. So this one, if x equal to 1, switch 0 to 1. You can just do sine of 1 divided by 1, and everything works fine without all that problem. The reason is this function is well defined at 1, therefore it has a continuity, therefore you can just calculate it with substitution. But this one, this function sin x over x is undefined at 0, and that's why we do. The limits are not always the same. Sometimes a small change to it really change the answer to a question. All right, so this is another example. We have a limit calculation. As you can see, it's a little more complicated as far as the representation. You have a degree 2 function in the numerator, you have degree 2 in the denominator. So then again, this is it's going to take some time, and you're going to calculate x squared minus x minus 6 over 6x squared minus 19x plus 3. And calculate the value for all these different values of x, because we'll have a problem. This question, if x approaches 3, if x equal to 6, if x equal to 3, the function is undefined. Numerator is 3 squared minus 3 minus 6 equal to 0. Denominator is 6x squared minus 19 times 3 plus 6. It's 0 as well. So we're having 0 divided by 0. Again, 0 divided by 0. That division is undefined. So we cannot do direct calculation. We cannot substitute x plus 3 and calculate it. So whenever substitution failed for a calculation of the limit value, we'll have to think about the process. So if x equals 3 is undefined, what about x not equal to 3? What about x is close to 3, around 3? So this is what we're doing. We try a couple number when x is bigger than 3. We try a couple number when x is smaller than 3, and those are the calculations. Right, on the in the book, they're already organized for us. But if you are calculating it by yourself, you may have to write down every calculation and be able to catch the steps so we don't lose track of things. So for example, this one, right? You're going to calculate 2.9 squared minus 2.9 minus 6 divided by 6 times 2.9 squared minus 19 times 2.9. That's what we're going to put in the calculator, and then plus 3. So for the first pair of number, when x is being 2.9, you plug in all the number into your calculator, and your final answer should be 0.29873. 0.29878. Should be the calculation. I did post a calculator just so you lost track of things and then you can try something else to calculate. All right, on the other hand, you go to with a textbook, online resources. One of them is called function calculator. All right, so we're going to put in this function we had. You can see it does a lot of things. The derivative calculation, it does find the limit for you. So here we go. The numerator was x squared minus x minus 6 squared minus x minus 6. There's a numerator divided by another function. It's 6x squared. So there's this burden of adding the function in if you want to use the function as your calculation. X minus 19x plus 3 plus 3. So first, let's see how do we calculate the function value. For example, we can calculate the value of the function when x equal to, see this number, 2.9. So if you have 2.9 and you show the number. So it does very exactly what you have on your calculator. It's 0.29878. And then the benefit of using this as a source of calculation is you can easily easily change the number. So the other number we're gonna try is 2.99. And this thing you can do it for any other function if you just change the definition of fx. Right, and then you can see this 0.294569, which is what we have in the book. And then you add more zero to it. And now we can see we're getting closer and closer. Maybe we add more. Right, because I think that's as close as we can get. All right, and then you can make x equal to a bigger number, such as 3.01. Let's calculate it. It's 0.29369. So all these numbers are saying to be 0.29 something, 0.294, 0.294, and we can try a number bigger than 3. We can try a number less than 3, and all of them are sent to be closer to the number 0.294. So I would say the limit is roughly 0.294. Yes.
So the correct answer could either be 2.99 or 2.999 or 3.0.
No, we are trying to find the limit when x approaches 3. So we want x to approach 3 instead of equal to 3.
So all of those would be the right answer?
Oh, none of them are the right answer. Those are just calculating the value of it when x equal to a couple of numbers close to 3. So you see 2.99 is really close to 3. 3.001 is also close to 3. But then they end up being a very close number to 0.294. So we say the limit for when x approaching 3, the limit is roughly 0.294. We see the tendency when x is further away from 3 and this number is further away from this number, when x get closer and closer, we see it. But then of course this computer system is probably going to do more, and this is a much more powerful tool. It calculated a limit for you as well, so we can just make x equal to 3 if that's a calculation thing. Which is the limit of the function is actually 5/17. This is the exact answer of the limit. But for now, we're not getting there yet. Right now, we're trying to figure out the value of the limit without going too much into the algebra. So right now, we know it's that value because we tried all these numbers. We try to make x as close as possible to 3 without equal to 3. Because if you knew if you make x equal to 3, it will be undefined, it will be 0 divided by 0. Okay, so this process of determining the limit is called a numerical method. Numerical analysis is one of the major subjects in math, one of the branches of math. All right, and we also have an analytical way of finding the limit. That is, how do we know? Because earlier we have 5/17. How do we get that number? That is going into the function. So this is our function. If you want to get the exact answer, instead of just a decimal number, all these decimal numbers, we get it plain and simple. We use our calculator, we calculate a bunch of numbers, and then we see the tendency, we see the number, all those numbers, where they are getting to. It looks like they are all getting to the number 0.294. That's why we kind of see the limit is roughly 0.294. Any decimal number, they may or may not be the exact answer. So 0.294 should be pretty close, but not the exact answer. If you want to know the exact answer, you have to understand the structure of the function. You have to go to the algebra of it. And that's what's slightly more analytical. So we will find the answer analytically if we want to know the exact answer of the limit. But we can try that. I mean, in pre-calculus, we might have done this before. So right now what we're doing is called a numerical. What we are doing is a numerical method. Numerical calculation. So this is one of the main approach we can do if we are not sure about the answer. And then you just do calculation. You calculate this, calculate x, you get closer and closer to 3. You can do 3.0001. As long as 3 is x is close to 3, not equal to 3. All right, another thing we can try is an analytical method. Right, so it's a different approach. That means you have to understand how the function is defined. Why is the numerator and denominator both equal to 0? Numerator and denominator of this function, they're both polynomial. Polynomial equal to 0 only when you have a x-intercept at that point. So meaning that the x minus 3 is a factor. So we can do this. So if we are trying to look at the numerator, so you see x squared minus x minus 6. All right, if you make x equal to 0, so x equal to 0. So what we can do, I guess the easiest way to do division is to substitute that. 1 and -1 and then -6. So there's the coefficient. Pull the coefficient out and enter 3. Drop down the 1 and multiply 3 and 1. To multiply 3 with 1, you have 3. Okay, and then we add the -3 with 3, then we have 2. And then we multiply again, multiply these two number again, and you have 6. So 6, we put it in the middle, right? And then you can see that -6 plus 6 equal to 0. This process is called synthetic division. Why are we doing synthetic division? Because we want to factor it. You see, it means after synthetic division, we realize that this, the whole numerator, is equal to, see that 1 and 2. 1 is for the x and 2 is for 2, so we have x plus 2 from this number. And then that 3 is a 0, so then x minus 3 is a 0, so we have x minus 3, and then we have x plus 2. Okay, so I'm doing, well, I hope that you still remember. Anyone remember synthetic division from pre-calculus? This is using synthetic division as a way to find out if I divide x minus 3 out of this polynomial, what do we have left? So after dividing the x minus 3, divide x minus 3 there, you have x plus 2, which is right here. So we find out the reason. The numerator equal to 0 if x equal to 3, because well, this is 3. 3 minus 3 equals 0, right? That's the part of the polynomial that equals 0. But then the rest, you see this one, x plus 2, if x equals 3. 3 plus 2 is 5. That part, that factor is not 0. This factor is equal to 0. This factor is the reason that the numerator equals 0. I mean, so there will be a same thing in the denominator. In the denominator, you have the same x minus 3 as well. So we would do the same. We do another synthetic division. So the denominator, you have 6, and then -19, and then 3. It will leave a little part because we're going to find some intermediate answer. We put in 3 here as well, and then 6 is drop the 3, and we multiply. If you multiply 3 and 6, you get 18. And then we're going to add -18 plus, -19 plus 18 is -1. Right, and then we again going to multiply 3 with the -1. We'll get -3. And then the -3 plus +3 equal to 0. All right, so that means that the answer to the division is this one, that's 6x. And this one is a -1. So 6x and -1 is the denominator. So the denominator part of it, so the numerator become x minus 3 times x plus 2. And then the denominator, this part, is going to be x minus 3 times the 6x minus 1. Right? So this is identical. This is identical to this. At least we were able to find a common factor. We still have the LIM. We still have the x approaching 3. Right, what we're doing is to change the format. We didn't change the function, we changed the format from this format to the factor format. The factor format is showing us numerator and denominator have x minus 3, which is causes to be undefined if x equals 3. But since they have a common factor, we're able to factor out the common factor and then just cancel the common factor. So the limit becomes still the limit. We still didn't do the limit calculation. We're changing the function to the one that's easier for computation. And then we have x plus 2, 6x minus 1. Right, now you can see that if x approaches 3, this is 3, that is 3. So the numerator when x equals 3, numerator is 3 plus 2. So now it's defined, it's well defined when x equals 3. The denominator is 6 times 3 minus 1. And this explains the answer to the question. The limit of the function is 5/17. Right. This method is an analytical method. You can see from the process is it's a bit time consuming. If you forget about consecutive division, you may not realize consecutive division is actually a tool for factoring. You do factoring quickly if you are familiar with the process. Right after factoring, we're able to factor out the part that's causing the problem. Cancel the common factor, and the rest works out nicely. And then 5/17 is roughly the 0.294. So your numerical calculation is giving you pretty much the same answer as an analytical method solution. The focus of the first section is trying to understand the numerical method. I was thinking about whether we should talk about the analytical method. A problem with the analytical method is that if you have a function that you have a tool such as polynomial, sometimes we can do factoring with consecutive division. But what if the function is defined by a trig function, like the one sin x over x? Probably no the answer is 1. And then the numerical method is actually a short method. Sometimes, because we have to try a couple numbers to see the tendency, sometimes it does take time, but it's a definite way to handle just about any limit. So we would prefer to introduce a numerical understanding of it, and then if it's possible, we would see how the function is being defined. Based on the definition of the function, sometimes it's easy to find the limit, sometimes it's slightly harder to find. So analytical method, if you can, the function itself. The numerical method really is all it is you'll be able to figure out the function value with your calculator. Any questions? I hope that we have some understanding of limit. And let's see. Okay, this is try to figure out limit of a function using the graphic way or numerical way. So let's talk about one more way to find the limit. So far we talked about 3 different ways to find the limit. The first one is numerically. Numerical calculation to lead you to the possible value of the limit. And second one is analytically. Okay, try to okay. Analytically, and then the last method is using graphical method. They all have their problem. If you want to do numerical calculation, you have to be have to understand your calculator well enough. Some people are able to define the function with their calculator, and you already define the function, you plug in the number. Like I was doing 2.9, 2.99, 2.99. So you have to use your calculator pretty fluently. Second way, if you're trying to solve figure out the limit with an analytical method, that means you have to understand the structure of the function. So sometimes it's like familiar with some functions but not familiar with some of the functions. So it really depends on personal experience. The last one is graphically find out limit. That means you have to be able to graph the function. And then again, that kind of depends on how much function graph we know. I think we're pretty familiar with the equation of a line or equation of a polynomial. But not familiar with the cube function or degree 5 function. So some of the trig functions that we learned in pre-calculus and some of them are not. So it really depends on how we graph things. And then again, for all these, we have computer as a tool. So if you're a little bit lost, you are welcome to try some of the tools that Crystal has shown you. Right. So I'm going to try them either way. This function is trying to find the limit of this function as x approaches 0. So you can see this function has 2 different definitions. This is what people call piecewise defined function. This function has 2 equations, so it's 2 p's. Visually, the graph is actually already given here. The first one is x plus 1. X plus 1 is degree 1, power equal to 1. The variable x has power 1. So degree 1 equation always has a straight line. So that is a straight line, which is on the left, x is less than 0. When x is bigger than 0, it's on the right. Like smaller side is on the left, bigger side is on the right. So x bigger than 0 is on the right side. It is a negative x squared. Right, positive x squared opens up. Right, negative x squared opens down. So this is negative x squared goes this way. We kind of anticipate the kind of graph as we were looking at the function. And then let's see how do we do it numerically. We want to do numerically, x is approaching 0, so x can be approaching 0 from negative or positive. So here we're going to do the function. So let's do it numerically, which is already, the answer is already in here. But let's see how we do it by ourselves. For example, if you look at the number line for x, okay, now 0 is right here, 0, right? So for x is less than 0, you will follow the first equation. So for example, you can have negative 0.1 and negative 0.001 and negative 0.001. So all these numbers on here, they're all on the left side of 0, so you all follow the first equation. For example, negative 0.1 plus 1, the answer is 0.09. So how do we do the calculation? So the first one, if x equal to negative 0.1, you'll follow the first equation, which is negative 0.1 plus 1. Okay, after you add it together with your calculator, you can see it's 0.9. Right, and then if x equal to 0.01, you have negative 0.01 plus 1. So the answer is slightly less than 1, which is 0.99. If x equal to negative 0.01, this is negative 0.001 plus 1. Because we don't follow the first equation for the left side of 0. And then that's what we have. So this is for when x is approaching 0 from the left side. And then what if x is approaching 0 from the right side? That means x is going to be a positive number. So x is positive 0.1, right? Positive 0.01. Even closer, positive 0.0001. Now, if it's positive, then x is bigger than 0. Then you have the calculations this way. So we have to calculate like this one. Actually, we're going to go further ones. So it's going to be 0.1, negative 0.1 squared plus 1, which is like I think it's in here, 0.99. And then if x equal to 0.01, so it's going to be 0.01 squared and then plus 1. Well, this is the negative. So 0.999, and then this is going to be negative 0.001 squared plus 1. And then do that calculation following the red formula, we're getting this number. But either way, on this side, it's getting pretty close to 1. On the other side, for the Weber one, closer to 1, you get closer to 1. You can see the total limit equal to the value 1, which is also what's in the picture. So looking at the function of that column, the second column is.
So, why are the red ones also negative?
That one's the negative. So the negative was on the outside. So then the x column is indicating that we're getting closer and closer to the function 1. So you would answer the question like this. We'll say limit of the function, limit of f of x when x is approaching 0, and equal 1. Right, you can see that this is all very close to 1 already. This f of x is representing that big thing that was piecewise defined. So limit of the function equal 1. So the 1 is a y value, and the 0 is a x value. So this is how we determine the limit, again, using numbers and using calculations. So that's what's called numerically approximate the limit, or numerical numerically calculate the limit. Now, how do we calculate the limit graphically? You see the picture? X is approaching 0. So on the x-axis, you'll find the number 0. And then you will go up virtually onto the graph of it. And then you can see which y value we're getting close to at x equals 0. Or you can move along the curve from the right wheel, all the way close to here, 1. And then from the left, your x value is go closer and closer to 0. When x get closer to 0, on the curve on the graph, the y is closer to 1. Basically, is if you want to graphically determine the limit, you are looking for the y value at that particular x value on the graph. Even though the x equal to 0 is undefined. X is not equal to 0, that's not equal to 0. So we have smaller than 0, we have bigger than 0, but still the y value is getting there, right? So limit is really a tendency. We don't care. You're doing the limit calculation. You don't care whether it's equal to 1 or not. You only care whether we're approaching 1 or not. So we're trying to get that tendency. Function center goes there. Any question? Right, so if this is a map and you drive all the way through that road, you're getting the 1, you know your target is 1. Even though it may be close, you can't get in there, but that's really what the road is leading to. So limit is really determining where the road is leading to, no matter the destination is close or open or not, but we know what it leads to. This is this example. I do want to mention one more thing that is, you guys know decimals? You heard of decimals? It's a nice graphing tool, and it is available whenever. So, for example, what if I want to see the graph and I don't know how to graph it? In this, on the board, the graph is already provided. In the book, it's already provided. But many times you look at a question, you want to see graphically how it looks like. But the question will you can calculate numerically, or it's not required to do graphing, but you just want to see it. And then sometimes I have a urge to say how each function behaves visually. So we can use decimals. For example, this is a piecewise defined. We have one piece of the function is y equal to x plus 1. X plus 1. That's how it looks like. That's what the function is when x is less than 0. So we say we only want the graph if x is less than 0. And then you can see that's left side of the function. Right, and then it's piecewise defined that the other piece is y equal to negative x squared plus 1. And that's the negative x squared plus 1, which has the left part and right part. But we don't want the entire function in our piecewise definition. We only want the part when x is bigger than 0. So we only want the positive half of the problem. So we're going to go in there and say, hey, let's keep the graph when x is bigger than 0. So there. So that's how it looks like. It's further, there's infinitely lengths on the line goes on the left, and the curve goes on the right. But in the center, essentially how it looks like. And you can also see that limit equal to 1. I mean, right in the middle, there's a 1. You can't even see the undefined point because the point is being graphed already, and a single point is like invisible. But still, we really didn't design the x equal to 0. There's bigger than 0, there's smaller than 0. So x equal to 0 is undefined in this situation. But at least we have a way to graph just about any function. So having decimals really made it possible for us to look at any function that we might encounter in class. That example. All right. So we have a couple of situations when the limit of a function can be determined graphically, numerically, and analytically. Yes, a couple of examples. But sometimes the function does not have a limit. So when does the function has no limit? What kind of situation could there be? We try to list those possibilities. Number one, the function f of x may approach different value on either side of c That's when the function have a jump, like it goes to 2 on this side, but of course, 5 on the other side. So you're gonna see 2 different side of it, and that's when the function is undefined. So right in the middle at C, we're like, is this 1 or is it 5? And then we can't, there's no consistency. The left side is not agree with the right side, then there's no limit. Later on, we might define one side, we can define the left limit, define the right limit, even though the two-sided limit does not exist. But for now, we see the limit does not exist if either side of it have different value. That's one situation. Second situation, the function may grow without upper or lower bound as x approaches c. That is when things explode. So, for example, when the function goes this way, so right at c, they were supposed to meet, left and right supposed to meet at the middle for the limit value. Somehow none of them are approaching anything. It's like an invisible wall making them go all the way up, and that's when we say the limit does not exist at c. The last situation is when the function oscillates as x approaches c. That's when the function goes. So you see the left side and right side supposed to meet in the middle to find the limit, but somehow as it goes, and you feel like they're meeting, but they're not. They're just going ups and down. So when things start oscillating around C, then you can't really guarantee because you see a big band right in the middle. Like sometimes trig function does that. You feel like they are meeting at -1 and 1, and you feel like they're meeting everywhere, and they're not meeting anywhere. So whenever they're not joining at a single point, we have an issue. So these are a couple examples for all 3 situations. Number 1, we got a piecewise defined function, and the left side of the function and the right side function are not meeting. That's the first situation. When the left side and right side is not agreed. And now what I can show you with the graph. The first one has, we already have the decimal sound, x squared minus 2x plus 3. Parabola, so it looks like for x is bigger than 1 for distance. Less than 1. Didn't work. Yeah, okay. That's the left side, and the right side is y equal to x, where x is bigger than 1. Okay, so that's how it looks like. So the left side is approaching the value 2. Left side is approaching the value 2. Right side went all the way to the value 1. So left side and right side are not joined together, so that the limit does not exist. The limit does not exist at 1, right? It has limit at 0. It has limit at 4. It has limit anywhere except 1. So at 1, the limit does not happen. The function does not. Any question? This is a piecewise defined function. You kind of have to use 2 different formula. There's one formula for the right, and there's another formula for the left. Left and right are not joining at one point in the middle. So the middle, at that single point, there's no limit. And any other point on the graph, they were fine. So this function, you see the statement. Limit of f of x when x approaches 1, it does not exist. You can change the setting, you change x approaches 0, then the limit would exist. So it's very important to identify the appropriate x value, and then the function value is the graph. So this is being determined by the 2 functions. So that was the first example. The second example, the function grow without bound. So we'll look at limit of 1 over x minus 1 squared, and you see how it is. This is determining limit of 1 over x minus 1 squared when x approaching 1. And you see why it would be a problem, because if x approaches 1, then x minus 1 is approaching a 0. x approaching 1, x is 1, like 1 minus 1 will be a 0. The denominator is approaching 0. So you have 1 divided by a number that's approaching 0. Of course, this number will be really big because 1 is being divided by a super small number. When 1 is divided by a big number, the whole division, the entire division is a really big number. That's why we're saying that it grows without bound. Visually, you're going to see something increase indefinitely. So see, okay. So 1 over this more visible. 1 is over x minus 1 squared. Okay, so that's how it looks like. And we can draw a vertical line at x equal 1 right in the middle. Right, so the x equal to 1, it's a vertical line. It's like an invisible wall. The whole function has a left piece which increasing. So if you're driving from the left all the way till get closer and closer to 0, and then it felt like you were getting closer and closer to a wall because it won't let you go. So the function goes all the way to that direction. If you're going to the right, and all the way going to the positive direction. And so either way, it's increasing. This y value is getting bigger and bigger. The y value, 5 and 10 and 20, get bigger and bigger. So left side and right side of the function is all meeting. So we won't be able to meet anywhere. This is another situation when the limit does not exist. Last one is the limit of sine 1 over x. And if you write it out, realize the denominator is going to 0 inside the sign. We have sine 1 over x. And then x is approaching 0. So we see that if x approaching 0, 1 over x will be getting really, really large on the positive side and small on the right side. So just look at 1 over 0. If x equal to 0.1, and then 1 over x will equal to 1 over 0 is 10. All right, then sine 1 over x will equal to sine 10. You can use your calculator to see what the number is. And then x equal to 0.01, and then 1 over x will be 100, right? And then sine 1 over x will be sine 100, and then that's another number. But the number will be all over the place. It's not approaching anything. You can make x equal to 0.001, that's 1,000, sine 1,000, and then you can go sine 10, sine 100, sine 1,000, sine 10,000. All these numbers, they're far away from each other. There's no tendency where things going. So that's why we're saying it's oscillating, because the entire function is not approaching any particular number. Visually, it looks like this. You can see the graph to get a better idea. Sine y equals sine 1 over x. So you can see the oscillating action. If they get closer, see what's going on. Right in the middle. You see, no matter how much you zoom in, x equals 0 right here. So right in the middle. You see, as we get closer and closer in there, whole thing is all oscillating and crowded together, and it doesn't really go go closer to any number. The sign is like a random number there. Sometimes in computer science, we even use this kind of function as a part of the programming for getting a random number with a negative and positive one. Because sine is really an interesting function that have a limit. Sine oscillates between -1 and +1. You see, the minimum is -1, the maximum is +1. There is no particular pattern. It's just go up and down, up and down. You see, as x goes to 0, there's no limit. When x approaching 0, there's no limit. Everywhere else was fine, right? Function 1 over x when x equals 0 is obviously fine. So if x approaching 1 or x approach 0.1, any other number non-zero, the full limit would exist. But only when x equals to 0. Any question? All right, for this kind of limit calculation, we have a special word for it. Remember, the limit does not exist on Weber. We're calling it dn E does not exist. So that way, whenever you see a question, let's calculate this limit, you try all the number and turns out does not exist, you will enter the end. So just remember how to enter the solution when the limit does not exist. Lastly, let's look at this example. You will feel like when you do your homework on web work, I feel like it has a lot different. It's very different from what we're talking about in class. Because what we're talking about in class is in general, what is the limit? How you have the limit. In the web work homework, it focuses a lot on this kind of limit. So we're doing a lot of limit calculation for one of the sole purpose, because we want to find the derivative. So we do a lot of this kind of division, and the numerator have a subtraction, and that's what's making it abstract. So sometimes people get confused. What are we exactly calculating? And with all these subtraction and division going on there. So we're gonna work on the web work homework together. So hopefully it's not too confusing. All right. So this one is a first example, which is vaguely similar to what you calculating the derivative. So we have a function, it's degree 2. The coefficient is not so nice. Normally the coefficient we give an integer, but now we have 1.5, 11.5. We can calculate f1, which is equal to 10, right? That is 1, that is 1. So negative 1.5 plus 11.5 equal to 10. So f1 equal to 10, f5 equal to 20. These are things that you can calculate by plugging the x value. We're going to calculate this one, right? So, and you can see those calculation number. We're making h approaching 0, which means it's going to be division by 0. Denominator h approaching 0. So we have numerator approaching 0, denominator approaching 0. So the question is, what exactly is that limit? And again, you have three different approaches. If you can, you graph it. And this question is slightly harder because the limit function is given by this weird little formula, and you're going to have to figure out what it is. And 2 is by putting a number, and 3 is by figure out logically what is the structure of function. That's even can be a little bit more detailed. So let's look at how we do it, and we can do a few examples of web work. All right. So this is what we calculate. All right. So first thing is we need to figure out exactly what we're doing. So we already knew f1 equal to 10, and we're gonna do a couple of substitution. We're gonna trade in switch out the actual number. So since f1 equal to 10, that means this is actually 10. We have f of x, that means this f1 plus h should be right, should be expanded based on that definition. So let's first write this f of 1 plus h minus 10, because we already knew f1 equal to 10, and divided by h. We're supposed to make the limit, we make h approach 0, but we'll hold on to that and then actually write out the calculation here. So how do we do that calculation? We first have to figure out what is f of 1 plus h. It equal to. So this is a part that I have students, they will skip it, they will feel like that is really abstract and hard to do. This is something the more you practice, the better understanding you have it. We know how to calculate f of x, which is already given there. F of x is given by this calculation. You're given the x value. You're going to take the x value, square it times negative 1.5, then plus 11.5 times x. So we're going to do the same. And first, putting the calculation, which is negative 1.5. And then whatever was the inputs, you were supposed to square. That's x squared plus 11.5. And then multiply by x. All right. So we're going to hold the x variable as the holder for any inputs. I'm leaving it blank. All right, and then what we're going to put in there is the input, which is 1 plus h. In the original definition, it's x, so we got x and x in there. But now we're not calculating f of x. We're calculating f of 1 plus h. So whenever the x occur in your formula, x has to be replaced. X is replaced by 1 plus h. So now we're writing 1 plus h here. Okay. Are we okay so far? So that's really how you write f of 1 plus h. So the steps is really tedious. It's very important to put in the princes, and then we're gonna work on how to remove all those pairs of princes. This one is easier. There's no square, so you would distribute the 11.5 times 1, 11.5 times h. That one you can distribute 11.5 directly. This one is harder because you have to know what is 1 plus h squared. As student, you always have 1 square h squared, and that was wrong. So make sure you have the 1 plus h squared correctly. Okay. So we're going to do this. So this is equal to negative 1.5. So I'm going to calculate 1 plus h squared. 1 plus h squared. This is actually 1 plus h times 1 plus h. That is a square, right? Square is the same value multiplied by itself twice. Are we okay so far? So we will multiply 1 with 1, so you will have 1. And then we'll multiply h with h, so we do have h squared. But we have something else. I mean, you can see if you multiply 1 with 1, that's first with first. If you multiply h with h, that's last with last, right? But then you also have the middle. H can multiply 1, and that 1 could multiply this h. So you're going to have the plus h and the plus h. We okay so far? Any questions? So we have a h here, and then have a 1 plus a 1 times h, and then h times 1. So there is a plus h, and then plus h. And then the other one I said we can just directly distribute. So that would be plus 11.5, because you're gonna multiply 11.5 with 1. You'll multiply 11.5 with h. So you're gonna have plus 11.5 times h. Okay. To make it easy, we can just have h plus h as 2h. Oops, the messy. So let's make it 2h. Okay, so we now can distribute the negative 1.5 to it. So I'm trying to do it as slow as possible so we kind of see how this part can be a bit detailed. So this is going to be negative 1.5 minus 1.5 h squared. So this is negative 1.5, this is negative 1.5 h squared, and this is negative 1.5 times 2, which is negative 3h. Right, and then plus 11.5. Plus 11.5. That was that one. And then plus 11.5h. So this is after you expand everything with this part. And we can combine these two. First two is a number, so we combine them. These two, if you combine them, negative 1.5 plus 11.5 is 10, right? So that was 10. And then we can combine these two. That's still negative 3h and 11.5h. They're all divided 2 on h. Number 1. Negative 3h. 11.5 minus 3 is 8.5. So that is giving us 8.5 H. Right, lastly, we have a degree 2 for H is minus 1.5 H squared. So this is what we have for f of 1 plus H. I hope I didn't make it actually difficult. We were able to follow what we actually. Right, and then that is just for what f of 1 plus H. I feel like that's a really abstract part of the calculation. Limit of f of this minus f of this. The second is f of 1, which is really a number, but the first one is really abstract. So you want to write down the abstract part, and then now you know what we are calculating. And then we're going to have to minus the 10, minus 10, and then over H. After that part is calculated. So this is equal to, you see we have a negative 10, we have minus 10. 10 minus 10 is 0, so you have 8.5 H minus 8.5 H. Maybe I can type it. So this is going to be 8.5 H, and then plus 1.5 H squared. A little bit better. Plus 1.5 H squared, and well, it was minus 1.5 H squared. Minus. So we simplify down to this point. Any questions so far? We haven't really attached the limit notation yet. Right now, we're simplifying this portion. So in order to finish the limit calculation, this is equal to limit of 8.5 H minus 1.5 H squared over H, and H is approaching 0. Okay. Now we can actually start calculating the value, and you can do it either way. Now we can do all 4 ways. Number 1, you can plug in H, negative 0.5, negative 0.1, negative 0.01 to find all these numbers. You can also use positive number, positive 0.1, positive 0.1. The blockouts, green box is what we are calculating. The variable is not X, it's H in this case. But you can see the tendency, it looks like the 8.5 something. So it looks like the limit is 8.5, and this is doing it numerically. So I would say it looks like the limit of a function, the limit value is 8.5 roughly. So from the numerical calculation, it looks like from the 0 to, I will estimate the limit to be 8.5. There's another approach, which is analytically. So numerically, based on your calculation on this, and also you're going to plug in the H value. Another way is to do it analytically. Let's analyze what's going on. So this is the limit. And you're going to factor the H from the numerator. So get H out, and you have 8.5 minus 1.5 H. This is 1.5 H squared. To bring the H outside, you still have one more H, right? You get 2H times H is H squared. And we also get a denominator that has H. So H is approaching 0. And then we realize the numerator and denominator, they both have H, so we cancel the H. And now the limit is no more division. So we got a limit of 8.5 minus 1.5 H. H is approaching 0. So if H is already 0, then 1.5 H is 0. So the final answer is 8.5. So we are able to determine the limit with an analytical method. Go through the whole function of it, find out the common factor. Cancel the common factor from the denominator, we know the limit for sure. That is the same as what we find out using the numbers. So function of number, actually a bunch of numbers. This is actually a pretty time consuming process. I think we do it But the orange one are the local calculation of it. It's pretty messy. And lastly, you can determine the limit with graphs. So this way, what we have is really division. So the denominator was, I'm using x because this is called what the decimals 8.5x minus 1.5x squared. So you can have numerator is 8.x minus 1.5x squared. Instead of h, I'm using x, and you can see how it is. Right, we want to know the limit of it at 0. So right there. There. 8.5 plus 8.5. That's 0, yeah. 0 is undefined, so you can see the value of it. It's right in the middle, but it goes to 5, 6, 7, 8. Right, between 8 and 8.5 if you look at it on the graph. So we can find the limit of the function using graph, using numerical calculation, the big table going on. Or if you're able to analyze the relation between the numerator and denominator, you will be able to cancel common factor and find it. And that'll be for today. I hope that gives you some idea, and then we'll do more practice again on web work. That way, people can handle the homework questions. I'll see you tomorrow. Thank you. Hope it's not too much. We okay so far?
Yeah.
I'm all right, but I don't know where hand is.
What's wrong with your hand?
It hurts for so much working.
You guys might see a little bit of paper function. We're using the clicker for attendance, so if you come in a few minutes late, wait after class, we'll do it on the.
Yes. I want to know, like,
Yeah, why?
I don't know why that messes with my head. Who would I talk to about?
Oh,
Do I just make like a maintenance report?
yes, I think the OCIS, they were supposed to fix this. There is a little, even now, I don't know what's calling it. Yeah.
Okay,
Sorry.
yeah, I'll do
Yeah,
that.
you can, I think you can, they're at the memorial. Right into the,
But I
what's the building's name? Memorial, what's the national? Yeah.
Yeah.
That's,
Graph was easiest, just gives you like a really.
it's
answer.
right next to,
But
right
numericals
next.
also
Sorry.
probably faster.
The registration building to the other side, enrollment building, north side.
North side of the.
I do,
Yeah.
but I don't know how to enter it.
You can email them, I think. It's probably help if you, on Georgia. In our email, school email, if you click on open a new email, just write help, it will automatically give you like.
Oh,
desk.
yeah, okay.
And just indicate this is the classroom Sequoia 142.
Yeah.
What's this called?
Well, I think it's probably room projector. I would, yeah. Yeah, I assume it's from the projector.
Yeah. You mean that is shaking, or is this? shaking?
Yeah, I think that is probably.
Okay.
Just gonna do the full line stuff.
I don't know why, but looking at it just gives me a headache.
Sorry.
No, it's okay. Yeah, I'll send him an email. Thank you.
This is a clicker question. Basically, I'll ask everybody when they did the pretest under review. If you haven't, please do it. So you guys did do this. Thank you. Do you still need this page or can we finish?
I think, can repeat,
The 8.5?
Yeah.
The 8.5? Is this 8.5? I think 8.5 is from, we got a -3h because the 2 times 1.5. The -1.5 times 2 is -3. So we also have the 11.5h from that one. So 11.5h minus 3h is 8.5h.
Okay.
This two combined is giving us the 8.5h.
confused. The H equals 0, you plug in 0, and you get.
Right, 1.5 times h is 0 because h is 0,
Yeah.
so that 8.5 is only 9. So the final answer is 8.5.
Tomorrow, we go to 1.2, or we're gonna?
Tomorrow we're probably gonna work on the web work 1.1 question. If there's nobody have a lot of issues, then we'll move on to 1.2.
Okay.
So that's how.
Yeah, so we should do like 5 questions tonight, and then in class tomorrow, then we'll be able to do some more questions.
Yes,
Okay.
and you can try the web work question. If you're able to do it, then we won't be able to spend too much time. But you can have a lot of questions, we'll do it together.
Okay.
The web work question.
So is that how the class set up, like, you go over the PowerPoint, we practice the problem, and the next day we do our work, and we will.
Yes,
the next day we
yes.
go on
So I will do the idea, the definition on PowerPoint. I will do a question on web work. If we have a lot of questions with web work, we'll do more examples. And then if there's not much issue, we move on to the next section, which start with the PowerPoint, and then if we can do those questions.
Yeah, I feel pretty good about this.
I've done some of the work, but I should have waited.
I didn't
I
try.
didn't understand, like, I was like stumbling to the right answer.
Well, it's always helps. I mean, you can see without learning it how much difficulty you have, and then
Yeah.
you'll see how much we understand after we know the.
That formula that showed up right there, I didn't know what that was, so I was just looking at it. How do you do this?
Yeah, those are function notation. My students always have some problem converting from the formula to the calculation.
Yeah.